So the last talk for the day one, would be by Aditi Raghunathan. Aditi is a senior PhD student at Stanford University and advised by Percy Liang. So she is interested in building robust machine learning systems with guarantees for trustworthy real-world deployment. And today she'll be talking to us about rethinking the role of data in robust machine learning. Over to you, Aditi.
I just wanted to add, she's also our alum.
Oh yeah, okay. Sure.
Okay, hi everyone, and thanks for joining. I know it's a bit late, so thanks for sticking around, and thanks Ravi sir and all the other organizers for inviting me here. And it's really a great pleasure to talk to you about some of the work that we've been doing at Stanford on robustness. And in particular, I'm going to talk about how data, or like things that we understand that from machine learning, from the standard setting where we don't think about robustness, can actually be quite misleading, and we need to do the opposite when we try to build robust models. So I'll talk about how data can actually be kind of a double-edged sword in machine learning in this talk. Also, just quickly checking, everyone can see my screen, right?
Yes.
Okay, perfect. So we've seen a lot of impressive results from machine learning lately, and there's a lot of excitement, which is why we have conferences like these. Like, we've seen these results, and ML is widely used in real-world applications as well, like translation, voice assistants, and so on. So we have all these impressive results, and we're trying to use ML in all these different applications. But let's look at how good is machine learning really in these applications. So here's a headline from 2015 that perhaps a lot of you are familiar with, where it was seen that facial recognition systems do not work very well on certain demographics like African Americans. This issue received a lot of attention, and it's been a few years since then, so you'd hope that things are better now. But in 2020, we see that facial recognition systems continue to make such mistakes, and this time a Black person was wrongly arrested. So I went back and saw what happened in 2015 and how did they address this issue that came up. And turns out that they removed the word gorilla from their captioning lexicon. So that was the fix they came up with. And I guess it's no longer that surprising that some of these systems continue to remain broken. Let's look at another domain, self-driving cars, which have also been quite a buzzword for a while now. And how good are self-driving cars, and why don't we see them around more? And in 2018, tragically, a woman was killed, where, among other issues, a machine learning model failed to recognize pedestrian who was jaywalking because it was only trained to recognize pedestrians at crosswalks during the training time. And there are also funny errors that I found when I looked up and here, because I don't want to start this talk on a very dark note. And turns out that this game was spoiled because the AI camera started following the referee's ball head rather than the football. So there's a lot of promise and a lot of excitement about the potential of using machine learning, but then the way we currently build our machine learning systems leads these systems to be very brittle. So what's going on here? Like, what's the core issue, and how can we make these systems more robust, especially since we're going towards a day and age where we're going to use machine learning in so many more different applications? So how do we typically do machine learning today? We collect a data set of examples, and we split this into a train and a test set. So we train on the training data, and we evaluate on this held out test set examples. So notice that we are only evaluating on examples that come from the same distribution P as the training data. Most of the benchmarks, as well as traditional learning theory and generalization, studies this question. And there are, of course, a lot of things that we need to understand about the setting. But this is not sufficient when we look at real world deployment, because what we care about really is this wide range of examples that the model could encounter when it's deployed. For example, pedestrians who could be jaywalking. And so the goal of robust machine learning, the way I think about it, is that we want to get good performance, not just on the exact training distribution, that the P that we got the training data from, but really a large range of examples, including those outside the data set distribution. And very quickly, how do we think of why robustness is important? So a natural setting is when we have adversaries in the play. For example, in all these applications, there are people who are going to try to subvert these systems, and they're not going to restrict themselves to the training distribution. So that you need to think about what to do when we go beyond that. And of course, safety critical applications like self-driving cars, we really need to think about all the corner cases and not just what we saw when we collected the training data. And finally, another important application is when we have different subpopulations, we want to make sure that we are fair and we don't propagate certain biases that exist in the training distribution. So we really need a way to think about how do we reason about going beyond the data set that was collected. So with that broad goal of robust machine learning, so there's a natural question here, like what are these range of examples that we care about and how do we characterize them? And then we can think about how do we make progress on getting good performance. So in this talk, I'll focus on two particular ways of defining these set of examples. One is based on spurious correlations, and models can pick up spurious correlations, and we want to design examples such that the model does well even when the correlations do not hold. And the other kind of more popular example is adversarial examples, where you could have adversaries that can perturb these test examples in some way, and we still want to do well. So these are two particular settings in which I'll show how we can try to think about robustness, and there are a lot of interesting lessons to be learned from these. And of course, we also need to think about different ways of defining these examples as well. So in this talk outline for both of these settings, I'll describe the setup first, and then we look at like how good existing robust methods are the things that we can think of to fix these issues, how well they actually perform. And then we'll see that they fail often in very surprising ways. In order to understand that, we'll try to capture that in the theory setting. And the theory setting is nice because we can actually analyze and come up with a solution and come up with some ways to fix the problem. And I really care about those solutions that we can actually scale up and see that they hold in practice and fix these empirical observations that we wanted to fix that we started with. So with that, let me jump right into the first part of the talk on spurious correlations. So this is joint work with Shuri and Pang Wei, who are both grad students at Stanford, and Percy Liang, my advisor. So first, the setup. Models latch on to spurious correlations. And the way we can think about these spurious correlations that there are misleading heuristics that exist in your training distribution, and they might work on most examples, but they do not always hold up. So here's an interesting example. So let's say we want to use machine learning to decide whether this chest X-ray has a collapsed lung or not. And you can collect a data set and then train a model, and things look quite good. Like you take a model, it would correctly predict that this has a collapsed lung, for example. So the average error is quite good. But if you look more closely, we find that the way the model is making this prediction is by using this treatment that exists in the training data. So the way the data was collected, most of the patients who were diagnosed were also treated. And so all these chest X-rays which had collapsed lung, or most of them, had this treatment, which is this tube. And that's what the model was actually picking on for making its prediction. And so as a consequence, the model did not detect untreated collapsed lungs where this chest drain was absent. And that's clearly the kind of demographic we actually care about if we were to use this system. So how do we make sure models do not pick up on these correlations and they hold on examples in the real world where such correlations might not hold? So here's another example in fewer medical terms that will be easy to think about, and we'll work through the rest of the talk. So let's say we want to determine if this bird is a water bird or a land bird. And as you might have correctly guessed, there is a spurious correlation in terms of the background, because most of the water birds are in water, land birds are in land, and machine learning models pick up on this spurious correlation. So when you have a water bird in water, so when this label matches the background, it turns out that the models do quite well and they get the right label. But if you had an image like this, where it is a water bird in a land background, the models tend to use the background to make the prediction and really get such examples wrong. So, like it has 40% error, for example, on such, water birds in land background, where the average error was only about like 3%. So if you just look at average error, which ML is really good at these days, things look great, but actually it could be latching onto spurious correlations. And even if you have a few examples like this, it turns out it's actually hard to get a model to learn not to use the spurious correlation. So to make things easy to think about, let's assume we're doing binary classification, and we also assume that we have access to the spurious attributes. So here we know that background could be spurious, and we also know the backgrounds of each of the image. So let's start with that. And so now, depending on the value of the background and the attribute, we can divide these data examples into 4 different groups. So you have majority of the examples where you have water birds in water or land birds in land, and this attribute matches the label. And for example, like these images here, but there are some minority examples where you don't have the correlation. So it's like reverse, so you could have some water birds in land and some land birds in water and so on. But our goal is that if we don't want to use the spurious correlation, we want to make sure the model does well on all such examples, not just those points where the attribute matches the label. So having defined these groups, we want to train a model that gets good error on all these different groups. Okay, so if you just did standard ML, turns out that that's not the case. So what can we do to improve this performance? So if you notice that we had all these different groups, but they all had different sizes, And so common intuition would tell us that what we should do is to just reweight the losses or reweight the points to account for the fact that we have some kind of group imbalance, and that would help us do well on all these different groups. This is the most standard approach that you could think of. So basically, you increase the weight on all these minority points, so you're kind of artificially forcing your model to pay attention to them, even though they're just few in number. And you could have more sophisticated approaches as well, like robust optimization on the training set, and they all are going to show similar empirical results as to what I'll show next about this simple approach of just increasing the weight on the minority points. Okay, so with that setup, let's look at how good this reweighting does. It's the same bird example as before, and in our training set, there are very few examples of water birds and land. So now we've tried to visualize what happens as we increase the size of the model and we do this kind of reweighting. So this plot visualizes the results. So first, let's look at the average error, which is this black line, and we see that as we increase the size of the model, which is what we do a lot in deep learning these days, we kind of just increase the size of the model and we see improved performance. And we see that that is true for the average error. So the black line goes down as we increase the size of the model. But when you plot the worst group error, which is this blue line, we see a pretty different trend. So we see that as we increase the size of the models, like the larger models actually perform worse than having fewer parameters or smaller models. So this is quite surprising and opposite to what we expect when we talk to people who do a lot of machine learning today, where there is a tendency to have bigger models and they work better, and we're using models with millions or trillions of parameters these days. But when you look at the kind of how well these models can be robust to spurious correlations through this reweighting process, we see that actually small models work better. We also looked at another data set where we have the celebrity database and we want to determine, say, hair color. And turns out that gender is a spurious correlation because there are very few, celebrity blonde males for some reason. And so here again, we see the same trend as before, where the average error goes down as we increase the size of the model, but the worst group error actually now increases again as we increase the size of the model. So the takeaway that we found that was quite surprising was that increasing the model size actually increases the worst group error. So in order to understand this kind of why is that happening, we wanted to create a simple example that provides some intuition. So we analyze a kind of high dimensional linear setting. And so this is I just wanted to distill out the two core factors that we found in our analysis about why why we observe this behavior that large models have high worst group error. So the first factor that contributes is that these spurious features, that is, determining whether the background is land or water, is much easier to do than actually looking at the features of the bird and determining whether it's a water bird or a land bird. So in some sense, kind of picking up the spurious signal is much easier to do than learning the core feature, though it does not work always. And the second factor is, of course, that there are a lot more majority points where the correlation holds compared to the minority points where the correlation does not hold. So I don't have time to go into the proof, but I wanted to give some intuition for why these two factors give rise to this kind of behavior that we observe. Okay, so let's say, this is what the data set looked like. Right? So if we just used the background to make its prediction, the model picks up on this spurious attribute and it gets all these examples of water birds and water correct. But it will get a few examples wrong, which is this water bird and land. And in fact, we've actually increased the weight on that point. So we want to really make sure the model fits that point well. And okay, so we really increased the weight on this point to make sure that the model does not do this. So we don't want the model to look something like this, where it gets a few points wrong. But why does this fail when we have large models? So though we have increased the weight on this point, why does the model still do badly on the test set? It turns out it's because when you have a lot of parameters, the model can really do something degenerate and overfit or kind of memorize this particular training example, which is the anomaly or something that's new of the water bird and land background. So it could learn something like this, where it really uses the background for most of the training points, but in a few minority examples, it does something complex and fits that particular point, but doesn't generalize at all with the test set. So it does not work on other such examples of water birds and land background. So in this way, large models, because they have the capacity, they can really overfit or they can cheat to get zero loss on the on the training set, but they are going to do badly on the test set on these particular examples. But what happens when you have smaller models? Now, smaller models do not have that many parameters, so they can no longer do this kind of cheating, which means that if a small model were to actually do this kind of using the background to make its prediction, it just has to get this particular point wrong. So it can't do that, like that complex overfitting. And because we have increased the weight on this point, the fact that it got it wrong would lead to high loss. So this small model has to actually get low loss and fit all these points. It has to do something that can actually generalize to the test set and learn something like this that actually uses more than just the background for making its predictions. So this is kind of the reason why when you have smaller models, when you try to do this reweighting, like you actually need smaller models to work, and intuitively increasing the weight should work and we should continue to use these large models, but turns out that's not actually the case because overfitting is a real issue. And in some sense, this should not really be that surprising because, like, machine learning, when we study, we all learn about overfitting. But in current practice, it seems to be like people believe that we don't have to worry about overfitting and really can use these big issues. But turns out that when we have these spurious correlations and different sizes of groups and so on, we really need to be careful about overfitting. And is there anything that we can do to still, make large models work apart from just reducing the size of the models? So recall that the two contributing factors that I showed in the previous slide was one is this, whether a feature is easy to learn or not, which we can't change. But there's also this group imbalance that maybe we can change, right? So the idea is that like we had a lot of majority compared to minority points. So can we artificially fix that by removing majority points? So we can remove the group imbalance by just removing a lot of the training data, which seems a little counterintuitive, but I'll show that actually does quite well. So what this says is this is what our original data set looked like. And now we tried to increase the weight on the minority points, but that didn't work. But instead, our theory said that what you should really be doing is to remove the majority points and really create a new data set that looked like this. And so this is an easy procedure to try, so we can continue to try this on the same data sets as before. So this is what we had earlier, where the worst group error increased as we increase the size of the model. But when we do this subsampling, where we really remove more than 90% of the majority points, basically, we see that now both the the blue worst group error and the average error start decreasing as we increase the size of the model. And now we're able to use large models by actually removing a lot of your training data. We see a similar trend in the celebrity example as well. Like earlier, this was a trend we had, but now when we remove certain training points, we are able to use large models and they work better than they did when they had the full data set. So now we're back to familiar territory where large models work better, but this really required the counterintuitive idea that we're removing so much of perfectly reasonable training data. So to summarize, what we found from our understanding of spurious correlations. So if you don't do anything at all, large models can have high worst group error. And it seems like what you should do when you have group imbalance is to just increase the weight on certain points. But you need to be careful because that might not always work when you have large models, because you can still try to kind of overfit, because it's so much easier to learn the background that the model can, and there are just such few minority points that the model can just do something complex. And changing the weights or changing the weight on the loss doesn't help because it's really got fit that point anyways. And so one thing that you could do is to not use large models, or use large models, but carefully remove points from your training data such that there is no group imbalance. And both of these seem to work in practice. But of course, they're kind of unsatisfactory because either we're sacrificing data or we're sacrificing complexity to address this problem. And there could be better things that we can do in the future. I don't know what's the format of questions, but should I just carry on with the next part and get to the questions at the end, or should I pause now?
I guess you can take the questions at the end.
Okay, cool. Okay, so now I want to talk about a different way of defining the set of examples that we care about, is adversarial examples. There's a different, very well-studied failure mode in modern machine learning systems. And this particular work that we're talking about is joint work with Michael, who is a PhD student at Stanford, Fanny, an assistant prof at ETA, John and Percy, professors at Stanford. Okay, so here's the framework. So it's very intuitive here, very simple to think about. So what we're trying to do is, you could have attackers that change inputs in some way when you feed it to a model, and we want to make sure that we do well even when attackers do that. Right, so here's an example. So this is a stop sign that a model would correctly classify. But now we can add careful graffiti-like stickers. So like if you and I look at this sign, it's very clearly still a stop sign, but a machine learning model would now call this a speed limit sign instead. So in this way, you can perturb inputs and you can cause your models to say something completely wrong. Here's another example. So here, by just having, so it's like this is correctly classified as toxic, but by just adding one careful typo, like you just like add an extra I here, and now you can fool your model to call this statement as non-toxic. And so if you have content filtering, you can basically get malicious content to pass through all these filters that we have based on machine learning by just adding such small perturbations. So abstractly, we have a test input, and if we were doing standard ML, we would only care about this example. But now we define a set of perturbations, and we want to do well even if an adversary can perturb this input to any point within the set of perturbations. And depending on how we define the set of perturbations, we can get different kinds of robustness, like this could be stickers, for example, this could be typos, and so on. So in this talk, I'll talk about a particular form of perturbations called pixel changes. So here's an example. This is an image of a lakeshore that is very clearly a lakeshore to you and I. And a model, if you just take an imaginary trained model today, it would correctly classify it as a lakeshore. But I can change each pixel by a really small amount to get the image at the bottom. So this still very much looks like a lakeshore to you and I, and in fact, the change is basically imperceptible. But the same model would call it a completely different class of laptop. Right, so basically, very small perturbations can also like fool your model, even if you don't even perceive them. And mathematically, this is a set of perturbations where each pixel in the perturbed image is close to the corresponding pixel of the original image by some small quantity epsilon. So I think this is an interesting setup to study because, like I said, this is really imperceptible. And because of that, it received a lot of attention because it's so striking. And a lot of papers have been written, but we still don't have a complete solution even today, despite all the research that has gone into it. So even when we try to be robust to this kind of simplest thing you could think of, like changing pixels and changing by a small amount, building robust models is incredibly challenging. And there are a lot of challenges. And in this talk, I'll focus on kind of some of the things that come up and why this is a hard thing to do. Okay, so like I said, a lot of work has gone in. And so let's look at what's the performance on a very standard benchmark of CFAR10, where we have these images and we want to classify it into one of 10 categories. And of course, now we care about robustness. So we first care about just what happens on the test set, but also what happens if you have an adversary who can perturb this test set. And let's say we look for perturbations, if we do kind of gradient descent or some ways of finding perturbations, and this epsilon is really small such that all these perturbed images are still very close to the original image to the human eye. So if we do standard training, we have done really well in machine learning so far and getting good performance on CFAR10. And the most standard thing that you could do will get you like standard error of like 4, which is great. But things are not robust. Now you can try to address the robustness by doing kind of adversarial training, and I'll get more into kind of what that really is about. And what we see is that the robust error does improve, but at the same time, the standard error has increased by more than 3 times. There's a huge increase in the standard error when we try to make things robust. And there's not just adversarial training. Over the years, many different variants have been proposed, and they all kind of show this similar trend where the robust error does improve, that's great, but the standard error of these robust models, that is how well these robust models do on the unperturbed inputs, is actually much worse. And this is a huge problem because we're making models robust, but we're also making them worse on the original task itself. So like, how do we make them practically useful? So first, let's try to understand kind of why this happens. Like, why does making things robust actually make things less accurate? So at a high level, what does standard training do? When we just normally do machine learning, we take the training input and then we want the model to get the right label. Now, into robust training, we care not just about the input, but we also care about the set of perturbations. So we generate perturbations on the training data, and we want all these perturbations to have the same label. So why does robust training, where we kind of add these perturbations, increase standard error? So one hypothesis is that the perturbations that we add are somewhat wrong or inaccurate. So for example, if, this is what happens. So like, suppose we had a lakeshore, but now we've introduced some perturbations which make this image actually look like a laptop, and standard training would have said it's a laptop. But when we're trying to do robust training, because we're artificially telling that the label has to be the same, we're giving wrong information to the model. But this is not what happens in practice, because really we are looking at perturbations that are so small that they're clearly label preserving. So we're not adding anything wrong. And in fact, for people who are familiar with ML, this is really like data augmentation. So like, if we add rotations or translations, it preserves the label when we train. We're kind of doing something similar. We're adding these perturbations which clearly preserve the label, but somehow they're actually making things worse when we talk about robust, when we think about these pixels and adversaries, which is quite surprising. So maybe this is because when you're adding these worst case perturbations, the model family that we're operating with is not rich enough. Right, so suppose our data set looked like this. So you had two classes and we only had linear classifiers. So now if we wanted to be robust and actually get all these boxes and not cross these boxes, then any line would have to be inaccurate. So it cannot correctly classify the points while also being robust. But if we had a complex nonlinear boundary, then we can be robust and accurate. So this kind of like model family issue is also not likely to be the explanation in practice because, well, we really use big neural networks, and also so they can express such complex boundaries. And also on the training set, we get zero error on the inputs as well as the perturbations. So we are able to fit the training data robustly. So it doesn't look like there is some kind of a complexity issue. So let's rule that out for now and think about, is there any reason why adding perfectly accurate perturbations, which should actually give your model more information, why does it actually make the model worse? So when we start thinking about this, the only thing that we could think of is that maybe we just haven't figured out how to train these networks well. And for people who work with neural networks, we know that it's very sensitive to hyperparameters, and maybe that's the issue here. But then in further study, we found that that's actually not the case, and this can be somewhat fundamental, and that this trade-off where we are adding accurate information with the hope of making the model better can actually make the model less accurate on the test set, and this can happen even in a convex learning problem where there's no optimization issues and we are fitting things well. So here's a simple construction, because I think it's quite interesting and counterintuitive that this could happen, so I wanted to kind of show why this could happen at all. So we work with over-parameterized models, which means that there are many more parameters than the training points. So all you need to think about is that there are many ways to fit the training data. For example, this was your training data. You could have all these different boundaries. You could have something like this. All of these do well on the training data. But which one is the estimator? What do we get when we actually train a model? And we can think of defining the estimator as one of the ways of fitting the data, but you're trying to, picking the one with the minimum norm. So like basically saying that you kind of, this is a way of defining out of all these ways of training data, what do you actually pick? And so this norm you can think of as the inductive bias, which tells kind of what model is actually learned when you train something in practice. So in this example, I show how this inductive bias can play an important role. And we work with splines where the inductive bias is to fit the training data by minimizing the slope changes. So that's the estimator that we learn. So here's this very simple construction. So suppose this was the ground truth. So you had two classes, and the true classifier was this kind of staircase structure. And here are some label preserving transformations that we could try to do when we try to improve the model. So we could have all these boxes, and clearly these boxes have the same label according to the ground truth. And we can try to get a model to obey that property and be robust to those changes. So now let's see what happened when we do standard training versus robust training in this setting. So suppose we had limited training data, and this is kind of what things look like. And if we just do standard training where we don't worry about robustness, so recall that in splines, we're trying to fit the data with minimum slope changes. So the way to do that is basically just use a line, no slope changes, and things look great on the held out points. On the test set, you get low standard error. Now let's see what happens when we do robust training for the same data set. So here, even though we got things accurate, we are not respecting that local kind of staircase structure. And so we actually try to fix that by adding these perturbations on the training data and now fitting this kind of perturb training data. When we do splines which minimize slope changes, this is the estimator that we would end up getting, the green one, which does badly on the held out points. So this is because of the inductive bias. So like if the way you fit the data is to minimize the slope changes, then this is the estimator that you would end up with. And we can see that this estimator has high standard error because now it gets all these points and the rest of the line wrong. So here's a simple example where with the best of intentions, we added accurate information that we wanted the model to obey. We just increased the training data. But because of the way the model uses the training data, you actually ended up being counterproductive and made the model worse on the rest of the points. So one way that I find convenient to think about this is that the standard training in this example captured the global structure. It got the linear part, but it did not get the local stability. And when we tried to introduce that kind of local structure, when we trained splines, we ended up compromising on the global structure because of the inductive bias of minimizing these slope changes. So this kind of shows why you could be in a situation where adding data actually makes things worse. To summarize the reasons for the trade-off for this kind of inductive bias, and really this happened because we had limited diversity in the training data. So if we just saw the entire line, if we had a lot of training data that spanned everything, then we won't be in the situation where you have to compromise on one of the two. And so with that, like, we can try to think about mitigating the solution just like before. And I can't change the inductive bias of deep learning because we don't understand it that well. So let's, like, there's an area of active research studies. So let's, punt on that and think about the training data, which is more straightforward. So of course, we can just try to increase the training data, but that's straightforward and expensive. Because if I were to do this for CFAR 10, I'd have to collect images from the internet and do some kind of crowdsourcing to get the labels. So instead, we looked at, went back to the theory and saw whether there's something cheaper that we could do, and we could actually try this out without, upsetting our advisors. And we found that, indeed, we found unlabeled data is actually sufficient in theory to mitigate this trade-off, which is nice because we don't have to do any labeling. We just have to collect images, which is much cheaper to do. And the algorithm that enables us to use unlabeled data to mitigate this trade-off is robust self-training. It's a very simple and intuitive algorithm that I'll quickly present as to you can see why unlabeled data can be so powerful for robustness. So let's look at the same example that we had before. So we had some same labeled data, but now we have a lot more unlabeled data. And I've shown this in black because we don't know their labels. So the first step is to just do standard training. Just don't worry about robustness at all. Take the label data, do standard training, get a classifier, and then generate pseudo labels or use a classifier to generate labels on the unlabeled data. So you basically get some standard ML model, and then you apply that on the unlabeled data to get pseudo labels. So what that would look like here is when we just do a training on that limited data, we get, without worrying about robustness, we get the blue line. And now we use the blue line to generate the labels of the unlabeled data. Now this works well because the blue line kind of gets the global structures, it gets things good on the unlabeled data, but we haven't dealt with the local structure yet. So let's do that in the second step, where now we do robust training that tries to capture the local structure, but we do robust training on not just the labeled data like before, but on the pseudo labeled data as well. So you can take any robust loss, like whatever you do for robust training, like adding perturbations and so on, but just do it on both the labels as well as the pseudo labels. So now if we do that in this example here, we can add these boxes, which is the way we do robust training. And now when we fit the data using splines, we actually get this red estimator, which is both robust and accurate. So to summarize, these were the two steps. First is just forget robustness, do standard training, and then use that to get pseudo labels. And now you do robust training on effectively much larger data set. So why does this work at all? It could sound like a free lunch, like where are the gains really coming from? And the key component here is that what we do in the first step, that is getting standard classifiers, doing standard machine learning, they really give accurate pseudo labelers. And I kind of started this talk by saying how ML is really good when the test distribution is the same as the training data. And these unlabeled data are not coming from an adversary, right? So they're coming from what we collect, and we can always collect them to be from the same distribution. And so whatever we have in the first step, the standard ML, is really accurate, and we can use that to get labels for free, essentially. And so maybe robustness requires much more data. We haven't figured out how to get robust classifiers. Well, but really all we need is unlabeled data, because we can get their labels for free using what we know about machine learning to start with. So in this way, unlabeled data is especially valuable for robustness. And we saw that in this example here. So we didn't have any extra labels. We just collected extra unlabeled data, but we're able to get both the local and the global structure. And we can kind of prove this more generally, that in this linear regression setting, this will always happen, that when we have unlabeled data, you would always provably eliminate these kind of trade-offs. Of course, that was all theory and splines and linear regression. And so what happens on deep networks, and this is the same example from before, and we just added more unlabeled data. And this is the table from before that I've added robust self-training. I just took adversarial training and we did robust self-training. And now we see that the robust error and the standard error both improve. So just to make it a bit easier to see, we see that the standard error has now improved by about 45%, but at the same time, it's not like we've compromised on the robust error. Really, the robust error has also improved. So in this case, we're able to kind of improve on both objectives and mitigate the trade-off. And Yeah, so in this talk, I spoke about why the standard error improved, because you're actually collecting more diverse data, and that helps you get more, information. And in another paper, we looked at kind of why robust error, this different objective, also improves. And the idea is kind of the same, that you're basically getting more samples for free. And they're very simple ideas, so you can apply it, to any architecture improvements. And even the state of the art right now is based on this robust self-training idea, because you can just apply to, whatever you improve in your architecture as well. And to summarize, and in general, when we think about, making things robust, for example, lighting changes or blurs and so on, what we typically think is that we should just add, this kind of data augmentation, or like introduce that to the training set. And this seems like a perfectly valid thing to do, because you're just adding more accurate data, and like all our intuition tells it should improve things. But we need to be careful, because that could actually make your models worse, and substantially worse in the case of adversarial examples. And this comes from the fact that it's not just data that dictates the performance, it's really how the model uses the data. And there could be some counterintuitive things that happen when we don't have enough diversity in the training data. But luckily, there is an easy fix that we can just collect more unlabeled data, and that fixes things. And this kind of holds both in theory and practice. And like earlier, people thought that some of these trade-offs between robustness and accuracy were kind of inevitable. But really, we showed that it's an issue of having less data, and that's somewhat easy to fix by using more unlabeled data. I just want to quickly check how I'm doing on time. So I have more stuff that I could speak about for 5 minutes, or I could wrap it up and take questions.
I guess we are already over time, maybe.
Okay, so then I'll wrap it up. Okay, cool. So I just, basically, there's a lot of things about how to even evaluate robustness when you have adversaries and these large models. And that's another area that we've been trying to work on, and trying to, get ways to actually know whether a model is robust without having to try and break it, and really get some sense of a provable security, which is a hard and challenging problem. Okay, so the takeaway is that, to summarize, is that when we have more data, or we have bigger models, and these are things that we typically do to improve performance in practice, but they don't always help, especially when you look at it more carefully through the lens of robustness. And unlabeled data is especially valuable for robustness by even the simplest idea of kind of self-training. And in this talk, or like in our work, we've seen that analysis of linear models generally provides very valuable insights in figuring out how to improve performance in practice. And like I said, very briefly, verification or getting provable notion of security for deep networks, which is kind of what we would need if we were to deploy these things in safety critical applications, that's extremely challenging. And for future work, of course, we need to think about more complex models and analyzing and seeing whether they can give the necessary insights to further bridge the gap. And of course, we need to think about more general and realistic, attack models, or like what do we do if these spurious correlations are unknown? And so all of these are, complexities that we need to deal when we think about building systems that we can deploy. And with that, I want to thank Google and OpenPhil for supporting a lot of my work, and my amazing collaborators. Thank you.
Thanks, Aditi. So we have some time for questions. Are there any questions from the panelists? Okay, maybe I have a question. So this is regarding the first part of your talk, where you were looking at the spurious correlations, right? Okay. So I was just thinking, would it make sense to look at this more from a causal modeling point of view, where you know that the spurious variable is not going to cause the label, for instance?
Right. So yeah, that's right. In general, so there are two aspects to the problem. So one is identifying the spurious correlations, and then given that information, given that this is a spurious correlation, how do we get a model to not use that? So I think causality is a very powerful framework in kind of thinking about how do we identify what are the spurious correlations. And really, this part of the talk was kind of focusing on, even if you knew what the correlation was, the background, and that doesn't work. And so we have the causal view of the world, which told us that the background doesn't, kind of cause the label. How do we actually get a deep network, or kind of modern ML systems to obey that? So both of these are interesting questions, and they're both kind of challenging in their own respect. Yeah.
Sure. And a related question. So, the table that you showed had these spurious variables as features, right? So, but often these are latent. You don't have them explicitly, right? So how do we handle that?
Okay, so a quick clarification. So they're not explicit features, they're explicitly annotated. So they can be like some complex thing, but they just annotate. Yes. And in general, yes, you're right. Like we don't always have those annotations. So we have some, so one thing like, was what we were talking about earlier is like using things like causality as like a pre-processing to try to figure out what these things could be and like maybe have some kind of human in the loop way to figure out like kind of distill the information on what's causal or not. But sort of a more straightforward, heuristic thing that we found that we could try to do is that at the end of the day, we want to make sure that your model is not like we have some training data and you want to make sure the model picks up on the training data in a right way and not just overfitting. And so one heuristic that we found was if you just train a model for a few steps and then look at what are the training points the model gets right and gets wrong, very often the model gets these kind of minority points wrong in a few steps of training because it has to be trained longer to actually overfit on those points. So that heuristic of just training a model for a few steps and then using that to identify which are the points the model could potentially memorize and then kind of fixing for that late, doing all these kind of reweighting smaller models and all of that to fix on that is something that we found helps in practice. We have some work at ICML this year, but that's not complete because like it's a heuristic and kind of the core problem is like what if your training data did not even include all the combinations of correlations that you could observe, like what if you never even saw a water bird in land, right? Like what could you do? And these are all interesting questions to think about. Yeah.
Sure, great. In the interest of time, maybe we'll close the question answer session here. There are some question answers in the chat box. Maybe if you have time, you can look at them and answer the relevant ones.
Okay, cool.
Great. Thanks for the talk, Aditi.
Yeah, thanks so much. See you.
Yeah. Thanks everyone for attending the day one of this conference. We have exciting talks coming up on day 2 as well. So we'll meet again at 4:30 p.m. Indian Standard Time tomorrow. Thank you, everybody. Have a good night.